Hello everyone, my name is Patrick Prochaska, and today my discussion presentation will be about enumerating chemical compounds in organic chemistry. We're going to be taking a look at a bunch of different techniques that allow us to enumerate the number of chemical compounds with a certain molecular formula. So here's a brief outline of my presentation for today. First, I'll talk about the fundamentals of organic structures, looking at some of the rules that we need to follow in organic chemistry. In part B, I'll be taking a look at enumerating cyclic compounds. We'll be using a lot of the same techniques we've seen in lecture using Polya's theorem. And finally, we'll be talking about enumerating straight chain compounds, both through exhaustive enumeration and through generating functions. Okay, so let's start off with some fundamentals of organic structures. So what is organic chemistry? So organic chemistry is defined as the fundamental chemistry of carbon-containing compounds. It investigates the patterns of bonding and reactivity of organic compounds, and it even opens up the possibility of creating new compounds. It's very important to understand the life processes and the different reactions that allow for living systems and organisms to live. Here are the examples of some common organic structures that we see: caffeine, glucose, and adenine. All of these structures here play a really important role in our lives. Caffeine is an example of a stimulant that you drink in your coffee. Glucose is a sugar which we need in order to survive. And adenine is actually one of the different compounds that is found in your DNA. So here are some basics of organic compounds. So atoms are these sort of elements over here. The little atoms are represented by letters, and they are held together by bonds. So they can be either bonded with a single bond, a double bond, or a triple bond. So that allows these atoms to go ahead and form bigger molecules. Each carbon, by rule, must form exactly 4 bonds to other atoms. So we could see here, this carbon, for example, has formed 1, 2, 3, 4 bonds to different hydrogens, and that's a rule. This carbon over here has formed 1, 2, 3, 4 bonds to other atoms around there. Each hydrogen must form exactly 1 bond to other atoms. So this hydrogen here forming 1 bond to other atoms, and those are going to be the rules for bonding. Okay, organic molecules can be represented as straight chains, as rings, or as both. So here is a straight chain compound on the left here. Here is a ring compound in the middle. Here is an example of what's called an aromatic ring on the right. A molecular formula gives a representation of the number of each type of atoms in a molecule. So let's take a look at this molecule over here. This molecule here has 4 carbon atoms and 10 hydrogen atoms, so we can represent it by the molecular formula C4H10. An alkane, by definition, is an acyclic molecule that only has carbons and hydrogens joined only by single bonds. So those are sort of the conditions for being an alkane: only carbons and hydrogens, only single bonds. So no double bonds, no rings at all. All alkanes have the molecular formula CnH2n+2. Now, in organic chemistry, we don't like to draw out every single atom because that gets a little bit tiring. So we have a few rules that allow us to save some space. So we represent bonds with lines. We represent carbons with sort of like the vertices. We represent hydrogens by not showing them explicitly. And we show other atoms by chemical symbol. So what this looks like is something along the lines of this. So we have 1, 2, 3, 4 carbons over here. We just represent that as 1, 2, 3, 4 carbons like that. All the hydrogens are sort of implied in the structure. We know that each carbon must form 4 bonds exactly. So for this carbon here, with only 1 bond to another carbon, we already know by definition there has to be 3 other hydrogens there. Same thing sort of goes for all of these other structures over here. This bromine over here, remember, it's not a hydrogen, so we represent it as a bromine like that. And then this benzene molecule over here, we have alternating single and double bonds. We would just represent it like that. Okay, cool. So let's now talk about enumerating cyclic compounds. So let's say here's an example of a problem. We take a look at benzene over here. It's an aromatic compound with molecular formula C6H6. One thing to note is that the positioning of the double bonds inside benzene actually doesn't matter at all. The reason is sort of there's a chemical reason behind it, but the most important thing here is that the positioning of these bonds does not really matter. Okay, so here is the question. So we have some aromatic substitution reactions that replace some of the hydrogens with halogens, such as bromine. So essentially, we take a hydrogen over here and replace it with a bromine. The question is, if we can replace any of the hydrogens with bromines, how many compounds can we make, and how many compounds can we make with each given molecular formula? Okay, so it turns out that the technique that we use to solve this problem is going to be using Polya's theorem. And this will be very, very similar to those necklace coloring problems that we did before. So how are we going to set this problem up? Well, what we're going to do is we're going to label our 6 carbon atoms on the ring as 1, 2, 3, 4, 5, 6. And we're going to treat having a hydrogen or having a bromine as basically 2 different colorings. So we're going to have a sort of hydrogen color and a bromine color. So here are what the labelings of the ring look like, 1 through 6. And these show 2 different colors of carbon-2. One with a hydrogen attached is a hydrogen color, if you will, and the Br attached would be a sort of bromine color. Okay, so the way that we apply Polya's theorem is the first thing that we need to do is take a look at all the different possible permutations. Here are all the different permutations that we could have for our benzene ring over here. So including our identity operation, our different rotations here, R60 through R300, and our different flips. So we start with our identity here, which is just the benzene ring just as itself. All our different rotation items just sort of rotate our benzene ring around. And the different flips include either a flip along the sides or a flip right through the vertices themselves. So for example, flip 2, 3, 5, 6 over here just corresponds to a flip over here. So we could see 1 and 4 will flip, 2 and 3 will flip, 5 and 6 will flip. And then, for example, flip 1, 4 would just represent a flip down this axis over here. Now, what we can see here is we can derive a cycle index for each of the following operations over here. So we write out these permutations in cycle notation, and our cycle index is basically going to be an algebraic representation of our operation. For example, our z1 to the 6 over here represents the fact that we have cycles of size 1, and we have exactly 6 of them. So we're going to go z1 to the power 6. We'll do another example over here. For example, z1 squared, z2 squared represents 2 cycles of size 1 and 2 cycles of size 2. So the zi coefficient will tell you the cycle size, and the exponent represents the number of cycles of that type. Now what we're going to do is we're going to go ahead and add up all the cycle indices and divide that by the total number of operations that we have. So this is just our dihedral group D6. So it's going to be 1 over 12 for the 12 operations, and then adding in all our different cycle indices that we see. So that is going to be your dihedral group D6. Okay. Now the next step that we're going to do is find ourselves a pattern inventory, which is essentially a generating function which tells us the number of each different type of compound. So we have 2 different colors here, the H for hydrogen and the B for bromine. And what we're going to do is we're going to sub in the following into our cycle index. So H plus B will plug in for Z1, H squared plus B squared sub in for Z2. This is going to give us a sort of generating function that tells us exactly what we need. So once we sub in these forms, we'll get a form like this, algebraically, and we can expand and rearrange and get the following generating function like this. Now this generating function is actually very useful because it tells us exactly what problem we have. If we look at this, we could just look at the coefficients and read them off to determine the number of isomers. So for example, if we see that the coefficient of H4B2 is 3, that is going to indicate that we have 3 isomers with the formula C6H4Br2. Now if we add up all the different coefficients, notice that we get 13 total, because 1 plus 1 plus 3 plus 3 plus 3 plus 1 plus 1 is simply 13. Okay, and if we use exhaustive enumeration, we can actually just verify that these are all the different isomers with that formula. Here are the number of isomers for each one, and adding them up, we get a total of 13. So we see that by adding them all together, our generating function actually gives us the answer that we want. Okay, cool. Let's now move on to the bulk of our presentation, which is going to talk about enumerating straight chain compounds. So remember, an alkane is a compound that has only carbons and hydrogens formed together by single bonds. So What we're going to do is we are going to say, given a certain molecular formula, let's find the number of constitutional isomers that we can form for alkanes. So for atoms with 1, 2, 3, or 4 carbons, these are the different possible alkanes that we are able to form. Notice that we get one alkane with 1 carbon, 1 with 2 carbons, 1 with 3 carbons, and 2 with 4 carbons, because we can put this last sort of CH3 group, this carbon group here, either on the end or in the middle too. Now what we're going to do is we're going to start by using exhaustive enumeration to devise a proper technique for counting our constitutional isomers. So what we're going to do is we're going to start by deriving ourselves a nice systematic way of counting these molecules. What we're going to do is take a look for the length of the longest carbon chain we have, count the number of ways to add additional carbons to that main chain. Now be careful, there is a lot of symmetry, so what we're going to be doing is being very careful of repeats. So here's an example question. How many alkane constitutional isomers have molecular formula C5H12? Okay, so the way we're going to do this, first of all, is by exhaustive enumeration. So we're going to create ourselves a little chart to set up our work. Let's say we can have our main chain having 5 carbons, 4 carbons, or 3 carbons. Okay, so let's start with the 5 carbon case. So clearly, there's no extra carbons to add. There's only going to be one option, just the molecule by itself. Now, for the 4 carbon molecule, how many different ways can we add a carbon? Well, we have to essentially add a carbon group to either to any one of these different vertices. So how many ways can we do that? Well, in fact, there's actually only one way for us to do that. And why is that? Well, the first thing we notice is that if we add a carbon to the end over here, we are just going to yield exactly this compound that we have over here. So we cannot add it over here. We can add a carbon to this position over here. That is a possibility. And we can also actually add a carbon to this position over there. But if we add it to that position denoted by the star, you will actually get a repeat of the compound where you add it to the arrow. So in fact, we only have one possible compound that allows us to do this. Okay? Cool. For 3 carbons, exact same deal. We cannot add those carbon groups to the end. We must add them both to the middle because we add 2 carbon groups. So actually, we only have 3 constitutional isomers. Okay, let's try one more C6H14. We're going to do the exact same setup over here. For 6 carbons, just the original molecule. For 5 carbons, we can either add the carbon group there or the carbon group in the middle. For 4 carbons, we have to add 2 carbon groups now. We can either add them both to the same carbon there, or we can add them to different carbons. Right? Remember, we cannot ever add a carbon group to the end, as that will yield an identical compound. So there's going to be a total of 5 constitutional isomers. Okay, let's now talk about an extra type of problem that we can have. Remember, we talked about halogens slightly before. Halogens are atoms that can form one bond to carbon. So something like a bromine molecule, for example, chlorine, bromine, or iodine. Essentially, what we could do is we can replace a hydrogen atom in an alkane with a halogen to form what's called an alkyl halide. So essentially what we do is take a hydrogen on the alkane, replace it with the bromine. Essentially, we are adding a sort of labeling to our problem. So this is a type of chemical reaction that allows such a thing to happen. What we're going to do again is look for planes of symmetry to avoid repeating compounds. Okay, here's my question. How many alkane constitutional isomers have molecular formula C6H13Br? Okay. The exhaustive enumeration approach actually starts off exactly the way we did it before, but what we're going to do is start with each of these compounds of C6H14, the ones we exhaustively enumerated before. Now what we're going to do essentially is we are going to go ahead and figure out all the different locations where I could put a bromine and not cause any repeats. So let's start with our 6 carbon molecule. So I can notice here that I have one mirror plane of symmetry in the middle. So I can put a bromine over here, a bromine over here, and a bromine over here for 3 different options. Notice that if I put a bromine in any of these other 3 positions, I will just repeat those compounds due to the mirror plane of symmetry over there. All right, let's repeat for all the other constitutional isomers. So I sort of have a small mirror plane of symmetry between those 2 carbons there, which yields me 1, 2, 3, 4, 5 different places to put a bromine. For this molecule down here, I have one mirror plane of symmetry down the middle, which yields me 1, 2, 3, 4 places to put my bromine. For this compound, the next one over here, top right, I have a sort of three-way symmetry around that carbon over there. So I actually have only 1, 2, 3 places to put my bromine. Now notice I cannot put my bromine on this position because carbon can form exactly 4 bonds. If I put a bromine over there, carbon would have 5 bonds. That is illegal in organic chemistry. Now for this last structure, we only have 2 different possibilities because we have a mirror plane of symmetry here, mirror plane of symmetry here. That's only 2 different carbons. Okay, so that gives me a total of 3 plus 5 plus 4 plus 3 plus 2, or 17 constitutional isomers. Okay, and just to verify, this is what all of those constitutional isomers look like. Okay, now that we've talked about exhaustive enumeration, we are going to move on and talk a little bit about how we can derive a generating function for the number of possible alkanes, as well as a bunch of different organic structures like alkyl halides. So here is the chart that we just found out using our exhaustive enumeration. We can represent this as a generating function. By convention, we let the x to the 0 coefficient be 1, just to sort of represent the fact that there's there's one constitutional isomer with no carbons, just namely like a molecule that has 2 hydrogens, okay? Can we find an expression for this generating function that would allow us to compute this for higher values? The answer indeed is yes, but before we can do this, we must do some other computations first. Okay, straight chain alkyl groups. So the first thing that we're going to do is define what an alkyl group is. So we talked about an alkane. An alkyl group essentially is just a fragment of an alkane that only contains carbon and hydrogen. So it's essentially part of an alkane, but it contains one free bonding site to attach to other groups. So the motivation behind counting these is we essentially can put a bunch of different alkyl groups together in order to form an alkane. So these are examples of alkyl groups over here. You'll notice that, for example, if I take this alkyl group over here and then this alkyl group over here, I can sort of combine them at the free bonding site. Sort of imagine me combining these 2 parts together like that. If I combine those 2 at that site, I will go ahead and form myself an alkane. Okay, the general case for an alkyl group looks something along the lines of this, where we say R1, R2, and R3 are distinct alkyl groups as well. This is what we call the general case for an alkyl group. Okay, now the symmetry of alkyl groups is fairly simple because we can actually permute around all 3 of the alkyl groups attached to the central carbon atom, and we get 6 possible permutations. Cool? So notice that all of these 3 represent the exact same constitutional isomer, and therefore we have full symmetry around this central carbon atom. Okay, so let's go ahead, just like we did before with the benzene molecule, let's go ahead and use Polya's theorem to derive the cycle index for this operation. So here are all the different operations that I can form. I could have a bunch of flips, where I flip the positioning of 2 alkyl groups, and I have a bunch of different rotations as well as my identity operation. Here are all the different permutations. Here are the cycle indices that I get for each of these. Okay, so this is just our symmetric group, which is called S3, and that is our cycle index over here. Okay, so let's talk about creating first an alkyl group generating function. So not the alkane generating function right away, but the alkyl group generating function. So we're going to let a(n) of x be a generating function representing the number of alkyl groups with up to n carbons. So it will look something along the lines of this. What we're going to have is basically the ith coefficient is going to represent the number of alkyl groups that have I carbons. And we're going to let our first term here be 1. Okay, so essentially what we're going to do is this generating function. So for example, the an group here will represent our generating function, which will tell you all the different number of possible alkyl groups for 0 all the way up through n. Okay, the next step is we're going to be finding our pattern inventory using a recursive technique. Okay, here is the key insight for this alkyl group thing. So let's say we have this form over here. What we're going to notice here is we try to find an alkyl group with n carbons, and we're going to let this generic case here have n carbons, right? The key insight that we have here is each of these groups, R1, R2, and R3, are actually going to be alkyl groups in and of themselves. each of them having at most n-1 carbon. The nth carbon, of course, comes from the central carbon in the middle. What we can do, therefore, is essentially do a substitution where we substitute a n-1x, which is the generating function for the number of alkyl groups with n-1 carbons. That's what we're going to sub into our cycle index to obtain our pattern inventory, i.e. our generating function. So we're going to go ahead and sub in the following three functions over here. So a n-1 of x going into z1, a n-1 of x squared going into z2, and a n-1 of x cubed going into z3. This is basically exactly what we did with the benzene case before when we're trying to establish ourselves a pattern inventory. Now we're going to go ahead and plug this into our cycle index with some slight adjustments to obtain our final pattern inventory generating function. So this is going to be our expression for a sub n of x. So notice we've made a few slight changes over here. So the first thing we notice is we just subbed everything in, but we needed to do a few extra things. So this extra x term that we have over here accounts for the central carbon in a new alkyl group. So previously we were doing an alkyl group with n-1 carbons, but now that we've formed something with n carbons, we are adding in this coefficient of x to sort of shift over our sequence. And this kind of is in line with exactly what we were doing in class when we talked about our sum generating function. So multiplying by an x will shift our sequence over. The other thing that we want here is we still want our first term to be 1. So remember, by convention, we wanted our alkyl series to start with 1, sort of having a 1x to the 0 term. When you shifted over your sequence by x and multiplied everything through by x, you made the first term actually equal to 0. So we're just going to add a 1 in there to maintain the fact that we want the first term to be a 1. Okay. Now, what we can do here in order to get the final generating function for alkyl groups is we can sum up the xn term for each a sub n of x. So take the 0th term of the a sub 0 function, the first term of the a sub 1 function, add them all up. It is going to give you the following expression over here. So if you actually go ahead and evaluate this, you can do this in Mathematica or some other software. This is going to be the generating function sequence you are going to get. Let's do the generating function for the number of alkyl halides. We did this through exhaustive enumeration. The way that we're going to do this in this case over here is by looking at what exactly it means to be a primary, secondary, or tertiary of alkyl halide. So what we're going to do is we're going to divide this into three cases, and we're going to count the primary, secondary, and tertiary alkyl halides separately. So here are just the definitions for each of these, but it's actually not that complicated. What we're going to do to determine whether something's primary, secondary, tertiary is just look at the carbon that is bound to the halogen. So in this case, our halogen is a bromine. In this primary example here, let's take a look at our bromine and take a look at the carbon that is directly bonded to the bromine. This carbon here is bonded to exactly one other carbon atom, namely this one over here. So this one is a primary alkyl bromide. For the secondary one, take the bromine, look at the carbon directly bonded to the bromine. We are bonded to two different alkyl groups, two different carbons. That's a secondary alkyl bromide. And same thing for the tertiary. Look at the carbon bonded directly to it. Take a look, 1, 2, 3 alkyl groups sort of off that carbon. So that's a tertiary alkyl bromide. Okay, so what we're going to do is we're essentially going to use this central carbon here as a pivot point and do some permutations using our Polya's theorem and our generating functions once again. Okay, so let's start with the primary alkyl halide. So primary alkyl halide has a sort of general form here. This here, it has a general form there. This is that central carbon here. And this R group here is an alkane that has n-1 carbon atoms. Okay. So because we know that this whole alkane has n carbon atoms, we know that that R group there has to have n-1 because the last carbon is namely just that central carbon over there. So our generating function for the number of alkyl halides is actually just going to be x times a to the x, where we essentially just go ahead and shift our sequence. So if you kind of want to see what that looks like, remember that a to the x was just the sequence 1 plus x squared plus 2x cubed, and so on and so forth. Now h1 of x is just going to be us multiplying everything by x. So it's going to be 0 plus 1x plus x squared plus 1x cubed plus 2x to the fourth plus whatever. We're essentially just shifting the sequence over here because what we're doing by multiplying by that x is just accounting for this extra central carbon over there. So yeah, it's actually just the same as the number of alkyl groups, just that we're shifting our sequence by one carbon. Okay, so that's for primary alkyl halides. Let's now talk about secondary alkyl halides. So we have this general form here, a bromine bond to two carbon groups. And we're essentially going to do the exact same thing where we do a generating function for each of these two alkyl groups over here. Okay, so we have to, this time though, notice that we have full symmetry between those two groups R1 and R2. So what we're going to do is we have to account for those symmetries somehow. So the way we account for this is just our symmetric group S2, which has the following cycle index 1/2 Z1 squared plus Z2. If you're curious how we accounted for that, just notice that we essentially have two possible permutations. We can have the identity, which has R1 and R2 like this, or we could have the one where we permute the two groups. This has a cycle of two cycles of size 1, so this is going to be Z1 squared. This one here has two cycles of, one cycle of size 2, so this is going to be Z2. So our cycle index total is going to be 1/2 times Z1 squared plus Z2. So that's just using our cycle index in order to do it. So that's all we got our symmetric group S2 to do. Okay, now what we're going to do is first we're going to notice that because these alkyl groups here are bonded to the central carbon atom, none of them can just be hydrogens, right? Otherwise that would overlap with the primary case. So we're going to plug AX minus 1 into our cycle index. If you're having a hard time seeing that, let's take a look at why. So if we know that, let's say this is R1 over here, and this is R2 over here, this is our bromine over there, notice that neither of these two guys are allowed to be hydrogens. But if you look at our generating function, AX, we knew that AX was just 1 plus x squared plus so on. This one term basically represented a sort of alkyl group that only has a hydrogen with it, right? So no carbons, just a hydrogen. We want to eliminate that case because we strictly want R1 and R2 to have no hydrogens, right? We want them to have carbons. So we're actually going to plug in AX minus 1, which is just 0 plus x squared plus so on, just to sort of eliminate that case where we have no carbon atoms, okay? That's all that we're doing, okay? All right, so what this is going to look like is just plugging in AX minus 1 into our generating function. Again, we have the x term to account for that difference, and that's going to be our final answer. Okay, so that's going to be our generating function for secondary alkyl halides. Now, you are actually going to get a chance in the video for doing tertiary alkyl halides. That's going to be one of the discussion problems that you're going to get to do if you want to. Okay, so now we're making progress towards our discussion on counting carbon-labeled alkanes, and we have a few more housekeeping items that we have to do first. So what we're first going to do is take a look at the number of alkanes that has the molecular formula CnH2n+2, where one carbon atom has a label. So something that looks like this, we have a little star that represents a label, and this is actually a little bit easier than just alkanes, first of all, because it takes away a lot of the symmetry that we have in our molecule. We're going to be working towards removing that symmetry in the last part of this derivation, okay? So this is going to be, sometimes we call this an isotopically labeled alkane because we sort of replace a carbon by just adding an extra label to it. We call it like an isotopic label. And we remember, just going back quickly, that this is your general form for your alkanes. You have 4 different alkyl groups around a general carbon, okay? So this 4-way symmetry can be represented by the symmetric group S4. So remember when we did a 2-way symmetry around the secondary bromide, we did S2. This time we're going to do S4. I'm not going to write out the permutations, but that's what it's going to look like. That is our cycle index. Again, we're going to plug in our pattern inventory for AX because that each kind of R1, R2, R3, R4, each of those are separate alkyl groups. And once we do our substitution, this is what we're getting for our final generating function. So 1/24x times this massive expression. We're going to call this generating function p of x. Okay. Now, one kind of small thing that we're going to need to do, and we're going to see why exactly we need to do this label, is we're also going to take a look at the number of alkanes that we have that have a certain bond that is labeled. Okay, so what this is going to do is something that looks like this. We're going to label ourselves a certain bond. So let's say we just add a little label. We're essentially finding the number of constitutional isomers that we have where one bond has a label. So again, this is going to take away a lot of symmetry. Same thing as we did in the secondary bromide example here. We're going to sub in the counting series AX minus 1 for each of these groups here, because again, we want to ignore the case where R1 or R2 are just hydrogens, right? We want to basically have carbons on both chains. There's two-way symmetry around that one bond, so we use our S2 cycle index, plug in to get our pattern inventory, and this generating function is over here. So that is the number of alkanes that have one bond labeled. Okay, we are almost in the home stretch now. What we're going to do is we are going to essentially put it all together, combine those two generating functions, p of x and q of x that we just derived, and essentially figure out how many alkanes there are total. All right. In order to do this, though, there's going to be a quick graph theorem that you need to do this problem. I'm not going to prove it, but it says the following. It says, let T be a tree. So here we're representing graphs. These alkanes, they're basically trees, right? Because they're acyclic, they're connected. They're acyclic because they're alkanes. So we're basically, they could be represented by trees, and a lot of studies in sort of early combinatorics for chemical compounds use a lot of graph theory. But here's a little theorem that we have. Let T be a tree. If we let P star and Q star be the number of vertex and edge equivalence classes respectively, then P star minus Q star will be 0 if T has a symmetric edge, and 1 if T has no symmetric edge. A symmetric edge essentially is just an edge that splits the tree into two identical subtrees. Okay, so edge that splits tree into two identical subtrees. Cool. Okay, so for example, this is an example of a symmetric edge because we have two different trees. This graph on the right has no symmetric edge. I've colored everything really nicely, and you can see that you have 4 vertex equivalence classes and 4 bond equivalence classes. So we have 4 sets of equivalent vertices there and 4 equivalent bonds, including that symmetric edge. For this one over here, we have no symmetric edge. We have 4 vertex equivalence classes, 3 bond equivalence classes. So that's just sort of a quick demonstration by example of our theorem. So what we're going to do is we can sort of rewrite this equation as follows. So P star minus Q star plus S equals 1, where we let S be 1 if there's a symmetric edge, S be 0 otherwise. So essentially, same formula, just sort of rearrange with this value S. Okay, next up what we're going to do is we're going to let Pn and Qn be the nth term of P of x and Q of x respectively. So remember, Px is our generating function for the number of carbon-labeled alkanes. Qx is the number of bond-labeled alkanes respectively. We're going to let An be the number of alkanes with n carbons. So that's really the sequence that we're looking for here. So what we're going to do is we're going to sum over all possible alkanes, or trees in this case, to get this equation over here. The only thing that we need is this sequence Sn, which is the number of alkanes with n carbons and a symmetric bond. Once we get that value of Sn, we are going to be done. Okay, how are we going to find that value? Actually, it's not too bad. So let's say we have a symmetric bond with n carbons in an alkane. It's going to have this general form where we have 2 R groups around this symmetric bond that we have in the middle. Okay, so notice that each R group has to have n over 2 carbons in order to have that symmetric bond. And therefore, the number of trees with n carbons that has a symmetric bond, the number of alkanes, is just going to be a n over 2, which is the n over 2 term of the alkyl group counting series AX. Because all that we're doing here is essentially saying that we are taking the number of alkyl groups that have n over 2 carbons. We sort of take those two alkyl groups, put them together, And that's going to be exactly an alkane with n carbons and a symmetric bond, where we sort of bring the two bonding sites together and form an alkane. If you want to see what that might look like, let's say these are my two identical alkyl groups. So like that is an alkyl group that we have over here. We can sort of bring this together with another alkyl group here, join them together, and boom, combine those two bonds like that. And this here is your symmetric bond. And the number of alkanes with n carbons with the symmetric bond is exactly just the exact same as the number of alkyl groups with n over 2 carbons, because we're just bringing them together. Okay, so when we actually compute that, what we're going to see is our generating function is just going to be the following thing, ax squared minus 1. So two small corrections that we make to our generating function. This minus 1 term essentially allows us to make sure that we count 0 carbons, means no symmetric bond. So we correct for that there, because remember in the alkyl group, we count just the hydrogen as 1, but we don't want to count 2 hydrogens being tipped together as being an alkane, right? Because that's not really of interest to us. But what this x squared term essentially allows us to do is sort of shift over our generating function. So just to sort of illustrate that, let's say we have ax, and we remember this was like 1 plus x squared plus 2x cubed, right? So a of x squared minus 1, like that, is going to essentially square every single coefficient in our term. So subtracting the 1 gives us a 0, plus x squared, plus x to the 4th, plus 2x to the 6th, plus so on. What we do here essentially is now our generating function will skip every single odd term. And that makes sense. Remember, if you have a symmetric bond, you can't have an odd number of carbons, because you must have n over 2 carbons, n over 2 carbons here, and together they have to be an even number. Okay, so this x squared term just essentially shifts our generating function over. Okay, now that we've done that, we are ready for the grand finale. Let's put everything together. So we have this form over here. And our generating function in terms of ax is going to be just this form over here. So this first part here, the Pn form, subtract the Qn, add the Sn, that is going to be our generating function. Okay? And what you can do here is actually evaluate the first few terms of your generating function over here. So 1 plus x squared plus x cubed plus 2x to the 4th plus 3x to the 5 plus 5x to the 6th, 9x to the 7, 18x to the 8th. These coefficients here are just simply the number of alkane constitutional isomers that we have with a certain number of carbons. And you remember when we did our exhaustive enumeration, these are exactly the same numbers that we had. We had 3 with 5 carbons, C5H12. We had 5 with 6 carbons, C6H14. And from this generating function, right away, without doing any exhaustive enumeration, we get 9x to the 7, so 9 constitutional isomers with 7 carbons, and 18 constitutional isomers with 8 carbons. So see if you could do it. One of the problems that you'll get to do later actually will have you try using the recursive formula. You can create a recursive formula out of that generating function, and you could essentially find out for higher numbers how many constitutional isomers there are going to be. Cool. All right, let's do a quick recap. We did a lot today. We talked about fundamentals of organic structures. We talked about enumerating cyclic compounds. And finally, we talked about enumerating straight chain compounds. Okay, so thank you very much for listening. Here are my different references. Thank you very much for listening. I've attached some practice problems in the discussion forum, so feel free to take a look at those. Good luck and happy problem solving. And once again, thank you so much for listening to my presentation.